The recording. So today we are talking about section 6.3, and we're going to introduce the idea of logarithmic functions. So these are new types of functions that we haven't quite seen yet in the course. And it turns out that the definition that we're going to use is based off of something that we haven't quite observed yet about exponential functions. So before we talk about the learning objectives, let me sort of give you an idea of what we're going to be trying to do in Desmos. Okay, so let me remind you of what we've been doing. So we've been looking at functions that look like this. We usually put an A out front, but I'm just going to sort of keep things simple and make the A 1. We should remember that the b has to be a positive number, and it can't be 1, because if it is 1, then all we get is something like this horizontal line here, okay? So when the b is greater than 1, we get exponential growth, and the larger the value of b, the more growth we get, because to go from one step to the right, we would be multiplying by b. And then we can't have b being negative, but we can have it being something less than 1. And in those cases, we get exponential decay, going down like this. In each case, we saw that the domain was negative infinity or infinity. The range was 0 to infinity. If the a was positive, in this case, the a is 1, so the range here is 0 to infinity. And there's a horizontal asymptote along the x-axis, so it never gets negative, right? It never dips below this x-axis. Okay, so one observation that we haven't made yet about this picture that we're looking at here in Desmos is that it passes what we were calling the horizontal line test, okay? So if you look at this function, and everywhere we draw a horizontal line, horizontal lines will intersect the graph in at most one spot, right? Even though it looks like it starts sort of flattening out down here, it's just ever so slightly decreasing, and any horizontal line that you draw will hit this graph in at most one spot, okay? And that's true for any exponential function that we look at, all the ones that are increasing and the ones that are decreasing as well, right? The only case when that's not true is if b were equal to 1, but we were saying that's not an exponential function, that's just a horizontal line. So that would be the only case when we don't pass the horizontal line test. It looks like the camera paused out there on you guys. See if I can reset that guy. Okay. There we go. Okay, so when we have an exponential function, this guy satisfies the horizontal line test. All right. Does everybody can see the audio and hear the video? Give me a thumbs up, just because it looked like it paused up there for a moment. So, okay, thanks, Tom. Okay, guys, great. Okay, so we've got this exponential function, and we're seeing some properties that we should already know, and we've observed something new, namely that it passes the horizontal line test. And what we said, sort of the purpose of the horizontal line test was to identify functions that had inverses. So this function has an inverse, and we'll sort of look at it, right? So how do we find the inverse? Well, what we do is we swap the role of the input and the output of the function, right? So the inverse would have the following form: x is equal to b to the power of y. And there you can see it in white, right? This is what happens when we reflect that line in pink there across this line y equals x, right? We swap the roles of x and y, and we get that line y. And because we pass the horizontal line test, this line that we're getting when we do this reflection is now a line that passes the vertical line test. It's a function, right? It's an actual honest-to-goodness function. And we would normally find the formula for it by solving this equation, right? Like solve this equation for y. And it turns out that we can, but we'll just take it as a definition, right? So how will we define the function that is seen here in white? Well, the output is going to be y, And the function name is called a logarithm, so we'll denote that by log. The base b is important, and we denote that as a subscript of a b here. And then the input now is x, okay? And so when you write it in this format, it comes out as orange. And you'll notice that the difference between what you're seeing here in white and what you're seeing in orange is basically that you solve for y in one and the other you solve for x. Okay, so we have this new function, and we're sort of seeing that it's the inverse of a function that we sort of already know pretty well. And again, when the pink function here is has a base that's greater than 1, it's increasing, but remember, it could have a base that's like 1/2 or something like this, or something smaller than 1. In that case, then the orange function would also be decreasing as well, right? So for the most part, when b is greater than 1, our logarithmic functions have this same sort of shape to them. And two things you should notice about this logarithmic function that we're defining here is that the domain is all positive numbers, right, from 0 to infinity. And that's because the range of this function in pink was all the numbers greater than 0, right? So the domain here, we can only plug things in for x that are actually positive, right? And then the other observation that you should make is that because the domain of the pink function was negative infinity to infinity, the range of the orange function is negative infinity to infinity as well. So even though it looks like it's sort of flattening out to a horizontal asymptote, it is not, right? It'll get larger than any value that you would like as long as you zoom out far enough, okay? So we're observing a couple of things, that we have a function here, and we know what its domain and its range are, right? And they're the opposites of the domain and range for the function in pink. Okay, so what we're going to talk about first, our first learning objective, is sort of giving these two guys some names. So this is called the exponential form, and this one down here is called the logarithmic form. Okay, and you will be interested in going between the two of them, right? So we're not really interested in the exponential function, but this curve we're seeing here. And it turns out that you can sort of think about logarithms, and this is the way we'll sort of introduce them here, as just being like sort of a different way of writing down an exponential equation, right? So there's going to be an exponential form and a logarithmic form, and the first thing we'll focus on is going back and forth between the two of them. And so let me go ahead and write what you've just seen down on the screen here on the board, and then we can compare it to what we see on the slides in a moment, right? So we have something like log base b of x is equal to y means the same thing as b to the power of y is equal to x, okay? So that's what we're seeing in Desmos, right? And in fact, that's what we'll take the definition of this to be, right? Okay, so let's go back to our slides and talk about learning objectives for today and what will be sort of on the homework. Okay, so here are our main learning objectives. The first thing is we're going to want to go back and forth between these two formats, this logarithmic format on this side and the exponential on that side. And we have to go both directions, right? So log to exponential, exponential to log. And really you can sort of think about these sort of things as being maybe like if you say some sort of phrase, you could say it either in English or you could say it in Spanish if you'd like, but the meaning is exactly the same, right? So it's something like that going on here as well. You can take anything that's an exponential form and just rewrite it as something in its logarithmic form, and they just mean exactly the same thing, okay? And we'll use that information to evaluate some very simple logarithms, and we should be able to do it sort of without a calculator. However, there's no way for us to sort of test that on the final exam because your calculator will have a log button on it, so you should be familiar with how to compute logs, but we'll talk about how to evaluate them and how to do it without a calculator in some cases. And then we'll introduce sort of two really common notation. There's the common log and the natural log. And the reason we introduce those is that most of you going on to courses that might use some of the stuff from algebra will probably end up seeing something like the common logarithm showing up somewhere. And those of you going on to something like calculus or Physics or some of those more math-heavy ones, we'll see the natural log coming up more naturally. And you can convert any logarithm to one of either of these, either a common or a natural one. And most calculators, I think all calculators have a button for both of these. So you should be aware of where it's at and how to sort of plug it into your calculator. And if not, you can come to office hours or come by on Monday or something like that. You can schedule an appointment with me, and I can show you how to do it on your calculator. Okay, but be ready on the final exam to do that sort of thing. So those are our main objectives for today. And then in 6.4, we'll talk about, again, the graphs of these logarithms. And then the cool thing will be sort of 6.5 when we start looking at properties of logarithms. And we'll do one example at the end of today that sort of shows us, you know, maybe why we would be interested in logarithms, or I guess more historically, why were people interested in logarithms to start with? Okay, had to do with sort of astronomy and making calculations with large numbers. Nowadays, they're important for other reasons, but we'll talk a bit about that. Okay, so here is basically what I've written on the board, just in terms of a formal definition, and this comes directly out of the textbook, right? So really, we're defining the idea of a logarithm base b of a positive number x, okay? And here's the format we'll use: log base b, and then we put parentheses and we say of x. And we can only plug in positive numbers into this logarithm. And that's a reflection of the fact that we saw the domain was 0 to infinity. Okay, so we saw that sort of in the graph. And what we look for is an output of this function, right? We're going to call the output y. And the way you determine the output is you try to think, okay, what do I need to raise this base to, this b, in order to get back that value of x? Okay, so what should I raise b to in order to get this value of x? And we just sort of take this as an equivalent statement, right? So this is, again, the logarithmic form, and it means exactly the same thing as b to the y is equal to x. So if you see this statement, you can go over here, and if you see a statement like that, you can come back in this direction. It's just sort of two ways of saying the exact same thing. And there are, you know, reasons why we might want to phrase it in one way or the other. And then the last thing that we observed was that, okay, the range is negative infinity to infinity, even though the graphs look like they sort of flatten out, right, and they slow down, they're not increasing very much, they do go all the way from negative infinity to infinity. Okay, and because this is important enough, I'm going to sort of leave it up on the board, and then once you guys have had enough time to sort of write it down, just give me a thumbs up, and we'll move on to doing some examples of using this property. Okay, and I would say about half the questions on the homework for this section, 6.3, are really just going back and forth between the two, okay? So if somebody gives you something logarithmic, go back to exponential and vice versa. All right, and since there's like 17 of you guys, I'm gonna wait a little bit just in case people want to put this into their notes. And also, if you're trying to absorb it, right? So if you have a question or something, or you just want to read it, go for it. I guess I omitted one key feature here that we should mention. Because it's a base, right, and it's an exponential, the b has to be positive and it can't be 1. And the reason it can't be 1 is because it didn't pass the horizontal line test at that point. You couldn't actually write out an inverse, right? The definition wouldn't make any sense. And that's because 1 to the power of anything is just 1. Okay, so I think we've had a good number of thumbs up here, and we'll move on to the next slide. So here's an example, right? And hopefully you can still see this. You know, we have it sort of written here on the board, but what we want to do is take this thing here in logarithmic form and just write it out in its exponential form. And I'm going to move this equation up just a slight amount so that you can sort of see it. In the meantime, try to identify what the base is for part A, right? So we'll work on A first. And we want to sort of think about what is the base in that case. Okay, and if you see what the base is for this one, just throw it in the chat. Yeah, I mean, the base when you're in logarithmic form is whatever that subscript is. Okay, so in this case, the base is 6. Okay, and that's going to be the first thing you want to identify. I mean, if you're on this side or this side, right? Because then to start rewriting it in this format, you're going to put the base first, which in this case would be 6. And then you want to identify what's the exponent, right? And the exponent is going to be the output of the logarithmic function, right? So what is the y in this case? Yeah, the output of the logarithmic equation in this case is 1/2. So that becomes the exponent in the exponential form. Okay? That's like the input to the exponential function, because again, we're just swapping the inputs and the outputs of the two functions. And then now you take what was the input to the logarithmic function, and that's sort of the output over here. So what's the x now? For this last one, there's one last number here. No, not quite 3. And remember, it's whatever is on the inside of these parentheses. Right? So what's on the inside of the parentheses in this case? Yeah, the square root of 6. And so hopefully what we've written down here in exponential form is something that's familiar. If you raise 6 to the power of 1/2, it's the same thing as taking the square root of 6. Okay? So this is something that we're talking about back when we looked at rational exponents. And so this is sort of even taken as the definition of the square root of 6. And here we can rewrite this guy in its in its logarithmic form. And the equivalent way of saying it in sort of the logarithmic language is that the log base 6 of the square root of 6 is equal to 1/2. And that makes sense because if you were actually just trying to compute, for example, if like somebody gave you some logarithm, they said compute the log base 6 of the square root of x, the square root of 6, what you should be thinking is, well, what do I need to raise 6 to a power of in order to get the square root of 6? And in this case, it's 6 to the 1/2. So the output should be 1/2, right? So you're always trying to think, what do I need to raise the base to in order to get this input? And that would be the output of the exponential. Okay, but in this case, they're telling us the input and the output, and we're just going back and forth, right? So that equation in A means the same thing as this, just a different sort of language. Okay, so let's look at B. What's the base in that case? Okay, great. That one's just 3. So then we get 3. What's the exponent? What's that y value? What should we have here for the exponent? Yeah, 3 squared. And then the output here is just 9. Yeah. And that should be familiar to you as well. If you just multiply 3 by itself, 3 squared, you get 9, right? So rewriting this exponential fact in logarithmic form is the same thing as saying the log base 3 of 9 is equal to 2. And if you were just trying to compute the log base 3 of 9, if somebody just said, compute the log base 3 of 9, you should be thinking, what do I need to raise the base 3 to what power to get back 9? And the answer would be 2, right? So you would say, oh yeah, the log base 3 of 9 is actually equal to 2. Okay. Okay, I think I got cut off from you guys for a second, but this is one direction, right? This is what I was saying, right? Go from the logarithm and the exponential form. And again, I mean, you'll notice this is really simple, right? So if you have this down for the final exam, you can get a few questions where, the step is just one step, right? There were some things like this back on the midterm too, where it was just one step. And I mean, it's easy to lose all the points, but if you just know the sort of the simple step, you can pick up some quick points on an exam, right? Okay, so we're not trying to solve the equation. We're not trying to determine if it's true or false. We're just converting it back and forth. Okay, so let's try another example. In this case, we've got one that's base 10 and one that's base 5. So I'll let you guys sort of try that on your own, and then once you have it in exponential form, just throw it into the chat, and we'll talk about the answer when somebody has it correct. And hopefully I'm just sort of like giving you guys enough time that at least somebody is, you know, come to the correct answer, and hopefully that gives you enough time to think about it. Again, you want to identify the base first, right? For this first one, the base was 10. For the second one, the base was 5. Okay, so cool. We had the base here being 10, and the base for this one being 5, right? That's the first thing that I usually think about. And then everybody's sort of writing out the correct answer for the first one. The exponent here is going to be 6. And then now we'll take that y value to be, I'm sorry, that x value to be a million. Okay. And you know, what this means is if I take 10 and I multiply it by itself 6 times, I'm going to get a million, right? And I left off an extra 0 there at the end. There should be 6 zeros because it's 10 to the 6th, right? Okay. And then the second one, as everybody's pointing out here, is that, okay, if I square 5, I get back 25, right? And so if somebody was saying, okay, can you compute the log base 5 of 25, you would say, okay, what do I need to raise 5 to in order to get 25? And the answer is, oh, okay, it's 2, right? Because this is true. And then you would say, okay, the answer would be 2 in that case. But in this case, these are our 2 answers, right? And again, they're 2 just familiar facts that are true in their exponential form. All right. So just going back and forth between the 2 ideas. And here we've seen our first example of one of our learning objectives, the idea of what we're going to call the common logarithm. So this is something you should be sort of aware of, especially on your calculator. Most of the time, this is the notation that your calculator will use. It's also the notation that will be used in the homework and most textbooks that you see, although there are some exceptions to this. So we say the common log is the logarithm whose base is 10. Okay, so when we have something like this, where we're looking at a base 10 logarithm, we call it the common log, and the notation we use is not this, like you might think. This would be sort of the more precise notation. This is precisely saying the base is 10. But instead, we omit the 10 and just write it as log of x, right? And it's similar to sort of what we do with square roots. Like if we were to write the square root of x, it's really the same thing as the second root of x, right? But usually we just leave off the 2. And if it's anything other than 2, then we put in sort of the number, right? And that's the way we do things with bases here. If there's no base to be seen, there's no subscript, it means it's base 10 and it's the common log. And if it's not base 10, then they'll put the number in, right? They'll be specific about it and they'll tell you what the actual base is, okay? So let's go ahead and rewrite this one in this notation here, right? So how would we rewrite 10 to the 6th is equal to a million in this new notation, right, in log notation? And I'll let somebody sort of post it in the chat and we'll go from there. Because again, this is a log base 10, right? Yeah, I mean, it's just exactly that, right? So log base 10 of 10 to the 6th is equal to a million. Running out of room over there. But yeah, I mean, all I'm saying is just don't write the 10, right? So in this last example that we had up here, we didn't really need to include that 10 there. I mean, if you see this question in a textbook or something like that, they would omit the 10. All right? So this is what we call the common log. And we'll also have another important logarithm called the natural log, which has a different base, the Euler constant e, but we'll leave that for a little bit later and do now an example of going in the reverse direction. So now we're going to start with something that's in exponential form, so in this format here, and we'll want to rewrite it in logarithmic form. And then we'll try to make sort of an observation about what's going on here, so that we can try to think about things a little more algebraically. But here, I'll let you guys sort of, again, just chime in with your answer for A, B, and C. And then as soon as somebody has it, we'll sort of just discuss the details of the solution. Okay, so everybody's got the correct base here, log base 2 for that first one. And then you're going to take the 8 as the new input because it was the output of the exponential sort of function up there. And the output should be 3. And again, the way you read this is, what do I need to raise 2 to get an output of 3? So 2 to the 3 is equal to 8. Okay, and well, we've got this one here with, it's a log base 5 because the base there is a 5. The output was 25, so that now becomes the input of our logarithmic function. And the output here, let's try to just think about this even without looking at the equation they're having. What do we need to raise 5 to a power of in order to get 25? Well, the answer is 2. So 5 to the power of 2 is equal to 25. Okay, so the last one here is a base 10. So what does that one look like? Here, you don't have to write the 10 in the subscript because the LOG is just sort of telling you that the base is 10. And if you do use your calculator to compute logarithms, if it says LOG somewhere, what they're talking about is the log base 10, right? And we'll have a formula to compute the log base, whatever we would like, in terms of the common log or the natural log. So really, your calculator only needs one or the other, but most of them have a common and a natural log, but usually not sort of a different base because there's a nice formula that we'll see in a later section called the change of base formula. But everybody has it right here. So we've got the log base 10, so we don't put any sort of subscript here next to the logarithm. And now the input is 1 over 10,000. And what do we need to raise 10 to a power of to get 1 over 10,000? Well, there's 5 zeros here, right? 1, 2, 3, 4. Wait, is it 4? Yeah, sorry. 10,000, there's 4 zeros. 1, 2, 3, 4. So we need to raise 10 to the power of 4 to get 10,000, right? And then if we want to get it as 1 over 10,000, we need a negative. So 10 to the negative 4 is going to be 1 over 10,000, so we should get here as our output, negative 4. Okay. So everybody has the right answer there in the chat. Just don't forget the negative 4, right? Okay, so just familiar things in exponential form being rewritten in their logarithmic form. Okay. Now, one cool thing that I want to point out here is this idea of these functions being inverses of one another, okay? So let me go ahead and just use my Blackboard for a moment. And I think we've had enough of the converting back and forth. And I want to talk about how we can solve some of those equations in a more sort of algebraic way, okay? So let's look at, for example, 10 to the power of x is equal to 10 to the power of x. This is a true statement, and it is now an exponential form. So let's go ahead and rewrite this in logarithmic form. So I'll give you guys a moment to try and write that in logarithmic form. It's a common log, okay? So there's a common log. And remember, it was this form of, that b to the y over x, or y is equal to x. So our input in this case would be 10 to the x. And what would be the output? Yeah, just x, right? I mean, because the exponent here is x. Doesn't matter which one you picked for the one that you were converting. The exponent was always x, right? So that's what you're going to get output. And you can think about it this way: what do I need to raise 10 to in order to get 10 to the power of x? Well, it's got to be x, right? It's got to be x. And here, one nice way to think about it is that the log base 10 and the function 10 to the x are undoing one another, right? So if I wanted to solve an equation that had an x up in the exponent, I can just simply take the log and it'll kick out the x for me, okay? So this is one reason why we're going to be interested in logarithm, but this is something we observed sort of graphically earlier. If we let f of x be the log of x, so log base 10 of x, and we let g of x be this function 10 to the x, what we've just seen here is that f of g of x is equal to x, right? And we can also do something where we look at the opposite as well, right? So if we look at g of f of x, it turns out that it's also equal to x, okay? And instead of going through the same sort of calculation, let me just write out what that would mean in equation form. So in this case, it would mean that you have 10 to the log of x is equal to x. And what we're seeing here is that these are inverse functions. They undo one another, right? So if you have a 10 to the x and you want to undo it and get the x on its own, you can take the log base 10 of both sides. If you have a log base 10 of x somewhere in your equation and you want to undo the log, you can take a 10 to both sides, right? And you'll undo that and get back your x. So these are inverse functions of one another. And that's why it's going to be sort of really helpful when we're studying anything that has exponential phenomena. If we want to solve a sort of equation that comes up there, we're going to need to have logarithms showing up in the inverses. Okay, so these are inverse functions. Let's just go through and, I guess, do one last example, I think. Let me see. All right, we were on this one. Let's do this one really quickly. And I think we'll then be sort of done with all of our examples of the first two learning objectives. So let's convert these ones over sort of hopefully pretty quickly. And again, what I was just sort of pointing out here is that directly from the definition of the logarithm, we can get the fact that the graphs will be inverses of one another. And that's something we observed graphically at the start of class. Okay, but I'll again let you guys just come back in with your answers for A, B, and C. So what do we have for A? Yeah, the base is 3, so this is log base 3. The input now is 9. And really what we're asking here is, what do we need to raise 3 to a power of, right? What exponent do we need to raise to 3 to in order to get back 9? And the answer is 2. Okay, so 3 squared is equal to 9. And again, if you were just trying to answer this question, what is log base 3 of 9, you would think exactly, okay, what do I need to raise the 3 to get back 9? And it's 2. Okay, Let's look at b. In this case, the base is 5, so this is log base 5 of what? What should we throw in between these parentheses? Yeah, just 125, and then the exponent in this case is 3. I mean, we don't even really have to think about, evaluating anything. It's just a matter of going back and forth between the two. This is the exercise on the homework. But it'll get a little more complicated in this, and we'll see that sort of showing up here in a moment. And then the last one, C, I'll let you guys write that one in the chat as well. This is the log base 2. And then something goes in the parentheses, and something is on the right-hand side of the equation. Yeah, so the input now is 1/2, and the output is -1. Okay, so it's log base 2, because that's the base, and I ask myself, what do I need to raise 2 to a power of to get 1/2? Well, the answer is we need to raise 2 to a power of -1 to get an output of 1/2. So again, any familiar facts that you have about exponentials from chapter 1 in that review should now translate over to facts about logarithms, right? So it's just sort of a different language for expressing some of those facts. But the properties that they exhibit are going to be sort of vastly different, and that's what makes them sort of both independently interesting. Okay, the last learning objective we had was the idea of the natural logarithm. And again, it's just a little bit of notation. Those of you going on to calculus, it turns out that for reasons of calculus, this one turns out to be sort of the most interesting and has the most sort of nice properties of all of the logarithms. And it happens when the base is e, right? So you'll see it showing up in calculus in a lot of formats there. But you should be aware of it. It's called the natural logarithm as opposed to the common logarithm. And it's when the base is e. And remember, that was at like 2.71 or so. And you should have a base e number on your calculator. And most likely you'll have an ln function, and the ln function is the shorthand for the log base e. So instead of writing log base e, they just write ln. And the way you read that function is the natural logarithm. And just as a reminder of what we just said a moment ago, these functions are inverses of each other. So if we have y equals e to the x, right, and y equals the natural log of x, then when we compose these two functions together, they cancel each other out. So the natural log undoes the exponential function whose base is e, Euler's constant, and e undoes the natural log, okay? And this will be really important for us in later sections. So we'll review this again, but it's going to be sort of the basis of solving some of these exponential functions. But at this point, you should just sort of realize that if somebody writes ln, means the base is e, or if they write down the natural log, then what they're referring to is the natural logarithm. Okay. And like I said, you only need to stick to one of them because all of the other bases, there's going to be what's called a change of base formula. So, mathematicians and physicists and, really science-heavy stuff usually tend to go to the natural logarithm, and then sort of just places that might be applying things like stats or something like that, or, a health sciences sort of course or something, will probably end up using the common logarithm. So it just depends on what your courses that cover material like this in the future might be. But anytime there's exponential growth or anything that can be modeled with exponential functions, logarithms will be playing an important role. Okay, so let's just see sort of maybe a different perspective on things, how we might be able to use inverse functions to solve an equation. But I want to point out as well that in some instances, we'll ask you to convert things over to exponential or logarithmic form, and there won't be numbers everywhere, right? You'll have to sort of deal with sometimes the base being a variable or the input or something being a variable. And here's an example, right? So here we're looking at this logarithmic equation. The natural log of x is equal to 8. And, the instruction here is to solve for x. What is the value of x that will make this equation true? And it turns out we can, basically solve for the value of x immediately by just converting it over to an exponential function, okay? So let me give you a moment to try to convert this to exponential form, and then I'll show you sort of an intermediate step that you can sort of think about as well if you don't like to just memorize things. Okay, so Reddy's come in with an answer here, the base being e, so that's correct. And e to the x, not right. Not what you wrote. You wrote e to the 8th, right? Because the exponent is now the output of the logarithmic function, so that's e to the 8th is equal to x. And you've solved for x in one step, right? You just converted this over to an exponential form, and now in a calculator you could type in the e button and then power of 8, and you could get out a decimal if you would like and determine what e to the 8 is. It's a gigantic number. Anything to the power of 8 is typically usually big, especially if it's something like 2.71. Okay, but you've solved it, right? And we're going to get to more complicated versions of these logarithms. This is called a logarithmic equation. And we're going to get to more complicated ones that we would like to solve as well. But here we saw that we could just solve it in one step. But I want to show sort of an intermediate step in between that may help some people sort of maybe understand what we've done. So you can start out with that equation. Let me just erase this for a moment. You can start out with that equation, the natural log of x is equal to 8. And what you can do is you can try to imagine, well, if I could undo this natural log, I could get x on its own. And if it was multiplication, we would do division. If it was addition, we would do subtraction, right? Those are inverse operations of each other. In this case, we should recognize that the inverse of the natural log is the exponential function whose base is e. So what we can do is take this equation and take e to both sides, right? So if e to the natural log of x has to be the same thing as e to the 8th. Right? In this case, I'm just taking, these two things are the same, so if those exponents are the same, this has to be equal as well. And then what we use is the fact that these guys here are inverses of one another, right? And like we said before, if I take e of the natural log, they cancel each other out, and I get x is equal to e to the 8th. And so that's the same thing that we would have got if we just took this equation and converted it right over to its exponential form. And you can think about all of these, examples that we were doing here by taking the log of both sides, right? So this first one we could have done in this example here by taking the log base 3 of both sides. And then the log base 3 would cancel out with the 3, and you'd get 2 is equal to log base 3 of 9. And that would be another way of sort of thinking about what we're doing here. But that uses this fact here that the natural log and e are inverses of each other. And you can go the other way around as well, right? I mean, you could just take the natural log of both sides of an exponential equation and convert it over as well. Okay, so here is just a quick example of something you might see in the homework. Okay, and then here's the last one we'll do today that's sort of related to any learning objectives and related to the homework, and then we'll just look at a couple of properties that we'll see in future sections and talk about maybe why people were interested in logarithms in the first place. And later on, we'll look at some applications, and that'll give us some motivation for why they're still interested in them. But we'll talk about, where interest came in these functions. Okay, so here we're looking to evaluate a function, and in this case, we don't know the actual output. So what we have to do is try to think about what the corresponding exponential form of this function would be in order to determine what the output would be, okay? And again, we're going to try and evaluate this logarithmic function. And just as a reminder, right, the base would be 3. And what we're asking is, what do we need to raise 3 to, right? What do we need to raise 3 to? What's the exponent here that would give us an output of 1/9? Okay, so if we're trying to evaluate log base 3 of 1/9, we want to ask ourselves, what do we need to raise 3 to a power of to get 1/9? Okay, so what goes in this box here? in this question? Well, not -9, so the negative would certainly move things down to the bottom, but 3 to the 9 would be a really big number, right? It would be 3 times 3 times 3 times 3. Okay, so Bria has it here. So we would need the negative to make things drop down into the denominator there. But 3 squared is 9, right? So 3 to the -2 is equal to 1/9. So this thing right here is actually -2. Right? So this is -2, and this is 2, so -2 plus 2 is just 0. So the answer here is 0. But I'm not going to write it in that format quite yet, because I want to use this fact and then sort of think about it in terms of some functions canceling out. So here you can think about this as log base 3, and 1/9 is 3 to the -2. Okay? And here, now, this is the log base 3. That's the base 3. Those two things cancel each other out, and you get -2 plus this 2. And -2 plus 2 is 0. Okay, so this is a sort of a separate way of thinking about it. I mean, if you'd like, you could just write -2 plus 2 and then equals 0, and you'd be correct. But here, I'm just rewriting the 1/9, saying, that's what I need to raise 3 to a power of in order to get back that value of 1/9. Okay, so again, the answer here is 0, right? The answer here is 0. And you should be able to do this without a calculator, right? I mean, on the exam, we're not going to be able to sort of ask you to do this without a calculator, because you'll have a calculator, so you could type in basically log base 3 of 1/9 plus 2, and your answer would be 0 in your calculator. But it's hopefully maybe helps you understand some of the details. And we'll get into things that are a little more complicated based on this later on. Okay, so this is all I wanted to say about the homework. Let me go ahead and show you what I think is a really interesting property, and it's the sort of the main reason why people became interested in logarithms in the first place, right? And the first people that really were interested in logarithms in some detail were astronomers, and so they were, mathematicians that wrote entire books based on just logarithmic tables, so things like this, right? So this is a nice little logarithmic table book, and all you can see in here are just calculations. This is like before the time of calculators, and people would spend, years and years making these little books, right? And the reason why is going to be the following property that we look at, right? So let's say you type into your calculator, somebody gives you a number x, and you type it into your calculator, and let's just use the common log. So you type it into your calculator, and you get the log base 10 of x is equal to some number n, right? So that outputs on the screen. And then they tell you, okay, here's a second number, y, and you type it into your calculator again, and you get a different number as the output, m. Okay, and what I want to look at eventually is what would happen if we were to compute the log of x times y. Okay? I mean, this is our goal eventually. But before we do that, let's just convert this over. Right? Let's convert this over to exponential form. So what is this in exponential form? Remember, the base is 10. Here the base is 10. But what's the exponent and what's the output there in the exponential form? What should we get for those two equations? So here's the logarithmic form. Here's our exponential form. Okay, let me give you a little bit of a hint. The exponent here is n. The output is x. What do we get for this one? Yeah, and the second one, the only difference is that we get m, right? So this is 10 to the n is equal to y. And from there, let me just point out a familiar fact that we had from exponents. So if we get 10 to the n times 10 to the m, this is the same thing as 10 to the n plus m. Okay? And 10 to the n is x, and 10 to the m is y. And if we convert this over to logarithmic form, we get the log base 10 of xy is equal to whatever the exponent is up there, n plus m. And that was log of x plus log of y. And what I'm pointing out here is this connection here. This on the right-hand side is equal to this on the left-hand side. And what we're seeing is that a logarithm converts multiplication over to addition. And it turns out that, you know, early astronomers that were sort of calculating orbits of planets and sort of tracking things carefully had to multiply really big numbers to get precise predictions. And that takes a lot of time and effort and precision. But addition is something that's much easier to do by hand. And so they would use logarithms to sort of simplify some of their calculations. We'll see them sort of showing up in different formats than that. But that's it for today. I'll sort of stop the video here, and we'll talk about the graphs next time.